So any program in execution is your process, right? So yesterday we discussed this. So before doing this, one more program I'll show you such that it's easy for you to understand. Okay. Okay. Let it be this one. So here what we did, here we are creating one fork function. So whenever you create a fork function, do you remember this program?
Yes.
Your voice is not at all audible actually.
Hello.
Hello? Yeah.
Yeah.
Do you remember this program?
Yes.
Okay. So here whenever you write a fork function, so it will create a next process. Now what happened on that day? We were executing both the functions, right? If function as well as else function. So once again, let me just execute this program. Now, what happened here? It is executing first child process as we have written it for some 10 times. That's why it is executing it 10 times. And after that, it is executing parent process and it is executing it at 1 second delay. Okay. So why that happened? Now, if you see here we have written one function called sleep. Okay. Sleep for 1 second. This is nothing but delay. Okay. Now, why it executed both the functions? Actually, whenever we are writing C program, either if should execute or else should execute, but it is executing both, if as well as else. Why this happens? Actually, what happens is, here, whenever you create a fork, two processes are created. Okay. Now here, when you write fork, ID will store the what you call PID, okay, which is nothing but process ID of child. Okay, so let it be somewhere around 3, 4, 5, 6. Okay, now the PID of my child is 3, 4, 5, 6. That means ID value. So here what happens? ID is equal to 3, 4, 5, 6. So it executed this function. Now what happens is, here after this fork, the whole program is copied into child. Now main program, parent program and child program, two programs are there. Okay, and this whole program will be executed for child first. Till you encounter either this till you encounter exit or return or actually exit only, exit function when you till you get that. So as we have not written, it is executing the complete program. Okay, so here when this full program, now this full program is into your child as well as your parent. Okay, now when you say child, in child the ID will be 0. Now fork contains 3 values. Either it can be a negative value or 0 or positive value. When you have a negative value, the process creation is unsuccessful. That means a process is not created. 0 is for the child. Okay. So in child, the ID will be 0 in child process and positive for parent. So when this ID is equal to 4, if ID contains some positive value, that means a child is created. Now, here this full program. Now, your parent program starts from main, but your child program starts from after it encounters 4. That means the 4 in child program, the whole program is copied into child also. But child program starts execution after this 4 function. So that means it will start execution from it. Now what I said, in child process, if the child is created successfully, the ID will be 0. Okay, so this PID is 0. That's why what we got, this if condition is true. in child process. So it executed this process 10 times and it skipped else. It didn't executed this else function. It executed only this. Now, once the function is finished, again it returned to your parent process. Now, in this parent process, what happened? We know that ID value is not 0, but ID value is 3, 4, 5, 6. So that's why 3, 4, 5, 6 is equal to 0 condition failed and it executed else condition and we got to print this function. Is it clear?
Yeah.
Okay. So that's why it is executing both if as well as else. That means what? Basically we are executing two programs simultaneously. We will have to visualize the same program copied into two programs. One is parent and the other is child. Okay. Now here this is one. Okay. So just to show you one more program I'll write. So this will be more simple. I'll not write if else anything in this. Now, here I am simply writing this function poke, and then I am writing one printf function. So how many times actually it should execute? Basically it should execute only once, but as we have written poke, one more program is created and that's why it will execute more than that, 2 times. Now see, it has executed it 2 times. Okay, and one more thing here, see what it is doing. As it has ended the child process, again we got this and we are executing this program. Okay, what I mean to say is here it printed this line X and after that it terminated that program and again it executed. That's why it is showing it on 2 different lines. Okay, now if I say here, if I increase the number of pokes here, poke, and then again one more poke. Now here this is creating, first of all this is main is your parent, then this is your first child. This is first child. Now the first child have again child. Okay, so this is from first child it created child process created next child process. Okay, that's why because this function will start executing. Now this is your first child, so that's why, or you can say this is the child process, and inside this child process it is creating one more child process. Child is creating next child process because this whole program will be copied into next program. So this is your child process function. Again this will be copied, again this will be created, and that's why this will have next child process. So just to give you clarity, what I'll do, I'll just copy this. So here, now what happens when you call this child function? From here it starts executing. So your child process will have this lines. Okay. Next, again it starts executing from here. Next child will have these lines. Next it will start executing and it will print this. Okay, so we are creating these many child process. One main function is parent function. It is creating child. Child is creating child again and again. Okay, so this will execute. How many times it will execute? Now if we see that, it is executing 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 15 times it's executed. Okay, so sorry, not 15 times, but 16 times it executed. 16 times in the sense 2 power n times. Why? Because 2 power 4 is 16. Okay, so fork creates 2 power n times output.
No.
This is about a fork function. So basically it creates a process. Okay, now coming to next thing here. Now today we will see some other topics along with this. Now when we have this a.out file created, okay, so we will have in this a.out also some memory segments will be there. Okay, so in that you will have memory for functions as well as for global variables in a.out file, not in in a.out file. So here in PCB I said you that we have in PCB symbol tables. So PCB contains even PCB process control block which is created in kernel space when you are executing a process. So PCB contains some different structure. So here in that, what does it contain? Was process ID, parent process ID, file descriptor, page table, signal disposition table, then process state, signal state, symbol table. All this will be there in PCB. Now this PCB in that symbol table, what does it contain is the address. Okay, address locations for function and global variable address. All those addresses will be present in symbol table. So symbol table contains address for address location for address location functions and global variable. Okay, so symbol table contains the address location of function memory. So whenever you are creating whenever you are executing a function, some amount of memory will be allocated for it. So that address for that particular memory location as well as for global variable will be there. The address of these particular locations will be stored in symbol table. Now here you have header files, the file headers will be there. Okay, in a.out you will have even file headers. file headers. Okay, so what does this contain? This is like, it contains, file headers contain file format types, file formats, and hardware architecture. Okay, so in a.out you will have even file headers. So that file headers contain file formats as well as hardware architecture. Okay, now what you can say? So here we have the file formats of .elf or any executable format. You can say exe something. So that file format as well as architecture. Now you can say that what type of architecture, it depends. Whether it is an Intel based architecture or ARM based architecture or Motorola based architecture, any different hardware architecture. We know that all the processors will have different architecture like microcontrollers. So depending on which machine you are using, the hardware architecture will change. So the information about that hardware architecture will be stored in this particular file headers. Okay, so now there can be something like you can have different file formats also. So you have one more term here called COFF, which is Common Object File Format. Okay, such that we need not worry about what is the format of your file. This is common object. Okay, but why we need this hardware architecture information? Why we need is because most of the systems we are using is based. Okay, now we are using this Intel based system, and but now if you consider your microcontroller, or if you consider the microcontroller, suppose you are using something like Raspberry Pi or BeagleBone or STM32 controllers, anything, something you are using, or some boards you are using like Raspberry Pi. Now those boards are not based on Intel, they are based on ARM, right? So the information regarding this will be stored in this particular files. Okay, why? Because this is Intel based system and this is ARM based system. Two different systems are there, and we are using some serial cable to just pass this information from Intel based system to ARM based system. Okay, we are using serial communication to pass this information. Instruction sets for both of these systems will be different. Okay. Now here you have one more instruction set. Okay, if we say instruction set, what does this instruction consist of? Instruction consists of opcode and operand. Okay, instruction consists of opcode and operand. Opcode contains a unique code. Okay, that specifies what is the operation it has to perform. And operands are anything like registers or any CPU memory location or addresses, anything it can be. Like you can, for example, here you can have an instruction move. Instruction move is to copy data from one place to another, or you can say not place exactly, but it can be register, address, or variables, anything. Now I have two registers called A as well as B, which is accumulator as well as B register. Now if I write here A comma B, so the information which is there in B will be copied to A. A and B, we both will have same value. Simply you are using a move instruction. So this move is opcode, executes what operation has to be performed, and A and B are operands. Okay, this is the file for, this is the format of your instruction. So generally what happens is when you are writing C programming first will be converted into your assembly code. Okay, and then from there the instructions will be given to processors. General C program, whatever we are writing. Now, if I am writing a C program, now this process we have written for this particular Linux system only. But suppose I want to execute this fork process, just now whatever we have written, process 1.c, I want to execute it on Raspberry Pi or some Beagle board. Then what to do? The same thing will not work there. Okay. So what to do then? Why? Because I want to execute the same program there. So in that case, what we need to do is we need to use different compilers. Okay. If you are using, because right now the compiler which we are using is for Intel based system. So we need a compiler which generates an executable for ARM based system. For every different ARM based system or some other systems, every system will have its own compiler. Okay, but then what happens, then you call this particular laptop as a host PC, and that ARM based system called Beagle Bone will be your target controller or target machine. Okay, which is ARM based, and you call this as cross compilation. Okay, now what we are doing is, here we will have, generally what happens when you are using some particular software, suppose Keel software, so inside that we will have a compiler which is compiling the code for us. So even though we are using our Intel based system, because of that software we need not install anything else, but directly it is compiling with respect to that particular microcontroller. Okay, so basically for every microcontroller or any target based machine will have its own compiler. Okay, now what I said, we just want to create this particular process 1.c for our ARM based system. Okay, in that case, this, okay, one more thing, here you call this as GCC, right? We are using a C compiler here. Okay, so this compiler, actually this is for GCC is GNU compiler collection. Okay, but this is for its own environment, which means that this is native compiler. This is for this particular system only. So this is native compiler. If you say BeagleBone or Raspberry Pi or anything, they will have some inbuilt compilers installed already. So whatever already in compilers are installed with your systems, those are called native compilers. Okay, and now we want cross compiler. Cross compiler is, we are using our laptop which is host machine, but we are creating an executable file for our target machine. So we need to cross compile this. We should not use this our native compiler, but we need to use some other compilers. Like now I will use one compiler for ARM. So my command will be ARM Linux -GCC process 2.c, process 1.c. Now this should not execute actually. Why? Because I have not installed it yet. Okay, command not found. Why the command is not found? Because this compiler is not installed in our PC. That's why this command is not found. Okay, so basically by using this particular, in place of only GCC process1.c, we need to add something like ARM Linux also. So using this, we are able to execute or create an executable for our target machine. Okay. Now, how to find this cross compiler? Now, how I will know that which cross compiler has to be used with which machine? So that depends on your boards which you are using. Now, if I'm using Raspberry Pi, so I can simply go on the website of Raspberry Pi and I can download the compiler for that. If you're using something like Beagle board or STM32, there the information will be provided on websites that where we can find the compilers. Okay. Other than this compiler, we will have to use one more tool called GDB. GCC we are done. Along with GCC, we will have, now this GCC is used for compile time errors. Okay, compile time, to find compile time errors. Now, whenever you are using this GCC and executing your C file, what is happening if you have any errors while compiling the program? We are getting some errors on our terminal, right? We are just okay, some printf semicolon is missing or some segmentation fault, something we are getting. So those all are the errors by compiling. We encountered while compiling. Now suppose there is sometime we can have runtime errors. While running the program, we may have some errors. So that errors can be found out by using a tool called GDB. Okay, this is nothing but debugger. So debugger executes the error in, not executes, but it shows the error while runtime, while your program is running. Okay, now how this is executed is, when you are using GDB, you can just execute it line by line, like we did in our microcontroller. In a Keel microcontroller, what we can do step-by-step debugging also. That means each line will be executed at a time and not a whole program. So that same thing we can use here by using a tool called GDB. Okay. So generally all this DCC, GDB and all related software will be, if you are using some particular pack of software, you call it as tool chain. Okay. So basically all this will be packed in one particular software and we call it as tool chain. Now here, so basically if we come to a conclusion, native compilers are the compiler which runs on the Intel machine. I am saying just an example of Intel machine, that's it, which runs on the Intel machine and executes its output also on Intel machine. But when you say cross compiler, it will run on Intel machine but execute output for target machine. Okay, so this is for what it is, native compiler as well as native compiler and cross compiler. So native compiler runs and executes for same machine. And cross compiler runs on Intel machine, for Intel machine or some other machine. I am just naming it as host machine, and executes on executes your option output in ARM-based machine or some other architecture-based machine. Here I am giving an example of ARM-based machine, or I can say an executes in target machine. Okay, so if we want to, now you can say that here how to install that. If we want to install it, simply we will have to use this sudo install ARM Linux GCC. Valid option -L try install command line option L is not understandable in combination with the other option. Maybe I have to remove space from here. See, it is installing your ARM Linux GCC now. So now in this system we have ARM Linux GCC installed, because previously it was not installed. Now it is installed. So now we can execute this program. ARM Linux GCC process 1.c. Again, here we have some problem. Do I need to give executed reading packages unable to locate package? Okay, there is some error called unable to locate the package. Even though it has installed it, we have some error unable to locate the package of ARM Linux. So we will see why we got this error. But sorry, it has not been installed. Okay, it is reading the package, building the dependencies, reading the information, but unable to locate the package. That's why it is not installed yet. Our system didn't install it. We will install it and we will see while we are running some different. Anyway, we are going to have this RTOS. We will be seeing device driver. We will be just installing anyway. Now, next thing. Okay, now coming to your PCB, which is process control block. If we want to see this PCB, so I said PCB contains your some information regarding process ID, then PID, PPID, file descriptor table, then signal disposition table, then we have page table, etc., etc. So if we want to see information regarding this, then how to see that? How to see all the information related to this? Where we can find this particular information of your PCB. Now if we want to find out that, then we will have to use some commands. Okay, I have to stop it. Now if we want just to type ps -ef. See, if you write only this particular command, we can find the full information. ps- gives you UID, PID, PPID, then you have time. TTY is nothing but your ports, and then time, which was created and then command. Okay, so all these informations we can see in your ps-ef. This is related to your PC. This is contained. That means whenever you are creating one output file, here you will have one particular line created in your PCB block. Will not contain all these things, but it will contain only one particular this line related to your file. Okay, one more thing you will have is one command called top. So if you see this top command, now this top command executes every second. Okay, every second this will be updated. Here you can see all the information, complete information you can see here. Now if you see here, one user is there, and then 164 tasks are sleeping tasks, complete all the tasks overall is 165, and only one task is running or two tasks is running. One task, actually we are running one task, and that is our terminal program, and then we have 164 out of this 165 tasks. One task is running and 164 are sleeping. Zero stop, the zombies are not there, and all this information like PID, user, who is the user, either root or the user, and then you have virtual system, CPU percentage, memory percentage, time, commands, all the information regarding this PCB we can be seen in this top. With this command we can see. Okay, even now from that time we are saying something like file system, file system, file system. What is basically this file system? File system is nothing but the collection of your directories. Okay, because from starting when we started all these things, we have different file systems we are saying, but we have not said what is this file system. So basically file system is nothing but collection of directories and subdirectories. Collection of directories, subdirectories. Okay, so this is file system. Now we will have two types of file systems. One is your real file system, and other is virtual file system, VFS. We'll have two types of file systems. Real file systems are nothing but those are permanent on hard disk, and virtual file systems are temporary, which are created on RAM. Okay, that means it will just have even though that particular memory or that particular what you can say, it doesn't, that particular memory doesn't exist, still it will be seen like yes, that exists. It will be like a virtual thing. Okay. Now, what are the virtual file systems we have in Linux? We will have three types of virtual file systems in Linux, which are virtual file systems, VFS, are stored in RAM. Okay, so they are not permanent. It's something like you can say artificial, or even though it doesn't exist, we are just showing it like yes, that particular thing exists. So we will have /proc and this as well as def. So all these are stored in RAM. These are available in VFS in Linux based system. Okay. Now, what information does this contain? When you say PROC contains the process information. Okay. So process information from user space of RAM and contents of PCB from kernel space of RAM. Okay. Now, if we want to just access this, we can use PROC of our system. But this PROC will reside on RAM. So if we see here, we can see a particular folder or directory will be there in the PROC. See, here it is. All these things are created on RAM. So whenever we are creating a process, one particular directory will be created in this proc directory. In this process directory, whenever we are creating a process, one particular directory will be created for each and every process we create. Okay, each and every process will create one directory will be created. Directory. Device. This is device, system as well as process. Every process. Separate directory will be created. Process block. Process directory. Now, what is this directory? So, when we are creating directory, even directory will have PID. Okay. So, we are creating some directory called new, but our device, our machine will understand it not by name but by PID. So, if we create a directory called new, then it will have a PID related to it, and that information will be understood by your machine that, okay, when we are using it with name, but your machine uses it with PID. Okay. Then here, so the file system, when it is created, sorry, not file, VFS, particularly virtual file system, it will create it with 2 bytes of size, the size of your proc virtual file system. Only I am talking about PROC, process file system. So it will allocate 2 bytes of memory. 2 bytes of memory on RAM. 2 bytes of memory is the size of VFS, virtual file system. Till now, do you have any errors? Sorry, doubt? Error, Sam. Everything is clear, right? Now, coming to your system, we can access, we can find out information about hardware devices here. So PROC is nothing but process. All the information related to process can be found out in process directory. When you say system, information regarding various hardware devices can be found in sys. Various hardware devices. Okay, now if we see here in our Linux system, what information does it contain? We can just open a file also. We see here device. We say here console. We will see terminal. No, not terminal. USB. TTY is nothing but your USB. Okay, so the device here is, we can see CD-ROM or DVD. Could not display. There is no application installed. Okay, so it is not giving us properties. Permissions are there, but the basic information regarding this is linked to block device, parent folder is device, and the name of this folder is there. So we will see some other. Yeah. I think it will not even open this application. We will have to see which particular application can open it, and we will. Okay, so we have not installed any application which can open these files. We will install this and we will see what is there in that particular file. So basically all the hardware devices can be anything like your USBs or any external device. The hardware information about that device will be stored in this field. Okay. Then we have system information. Now, what does this dev contain then? So by using this dev directory, we can access special function system calls. Okay, system information will be provided, or we can access it from system /sys. And okay, we can just execute one command also. We will try to execute. I have to close it, I think. 1 minute. Okay, if you say /sysfs, then it will show you whether it is a directory or file or something. So here it says that it is a directory. Now from this particular /dev, we can access the special function call. Okay, /device contains information regarding your system calls, special function system calls. If we see here, we will be able to access this or not. In this we have device where we can say, okay, will not be able to. Okay, just now we have opened that one and not system. Actually we have, okay. So this is your system. So previously I opened the dev in place of this. So here if you see firmware, here you have ACPI, DMI, direct memory interface, then memory mappings and all these things are there. In this, if you see ACPI, you have interrupt tables and everything. In interrupts, we have some different types of interrupts here, error, timer, then clock, all these. I think we'll not be able to open this. Open with text editor. Okay. We can't see anything here. We can see about error in that. I can see we can see error folder, error file. Open with text editor. No, nothing is there in this. Firmware. Then you have some other kernel. Kernel. You can see reboot, CPU. We are not able to see anything in this. Yes. IRQ are nothing but your interrupts. So only some information like 210 is written on this. So this is, that's it. It stores some information in this way. It is storing. See, edge. Some particular information is stored in some different form here. So basically, your system contains some information of hardware device. Okay, and devices already I said we can access some system calls through it. So that system calls can be Now in this also you can have, in this system calls you can have subgroups or subdirectories also. But basic system calls we can have for input output, or you can say universal input output. Output calls we have is like open, closed, then read, write, etc. Okay, now all these system calls are used for particular devices. With that particular device file, we will have this special file associated. Okay, and that will reside in. Now, suppose for example, you have something like one USB port. Okay, that USB port we call it as some device which is TTY0. Okay, that means USB 0 here we have. So this TTY0 will use some, now whatever USB port uses, some system calls it uses, right? Those system calls are nothing but open, close, read, write. You have some IOCTL function, then one or more, two more functions we have. Okay, so these functions which are related to this TTY will be stored in this device file. Okay, so these particular special functions which we can use with this device will reside in your dev directory. Now if I want to say that how to make sure that this is particular thing is working. Now if I am calling one application. Okay, so how I can say that that particular thing is requesting the device or the application which we are requesting. How to make sure that it sends the request to same application or same device. Okay, for that also we can use one particular file which is there in your device file, device directory. Okay. For example, if you say if you are using one particular application, okay, so that application can be having anything. What information you can send there? For example, I'm thinking actually. Okay, yeah, you have one. If you have seen in nowadays everywhere in any shop or any restaurant, anywhere you can use that card swiping machine, right?
Yeah.
That you call it as point of sale device. So there in that what information you have, it contains barcode scanner. Okay, it contains some information regarding your pointer or anything. Okay, basic information I'm just an example I'm giving. So now those information which is there in this POS device will be stored in your um, device directory. Okay, why? Because you are connecting that particular device to your PC, so that will create a particular POS device directory for your that directory will be created in our system under this device, and what operations you can use on it, all the informations will reside there. Why you are saying it will create in our system? It will create that only if you are connecting it to our PC, and that generally we are connecting it through USB port. Okay, serial port. So the information, so you are saying that we are using a serial port. Now again, if you are using a serial port, you can have different serial communications, right? So we will have to say that we are using a serial port, which is a USART or UART device, and it is connected to one particular USB 0 or USB 1 something, or in Linux we can say TTY 0, TTY 1 something. In that particular folder, device folder, we can see all the information if we are connecting through whatever chain we set. Okay, why? Because here all these things has to be known. Why? Because our device cannot communicate directly with our hardware. So that POS device becomes our application. That application cannot directly talk to our machine. It will have to come through a proper channel. So a proper channel will be created. Each and every device, hardware device, will have a folder with in this dev file, dev directory.
Okay.
Is it clear?
Yeah.
So what this device file will do? Device file will access like a link between your device driver as well as your application which you are using. Now, We will just see one more program. You understood fork, right? So I need not write one more program for fork, or shall I write?
Yeah, I understood.
Sorry? I'm passing switch to ID to a switch case. Okay, so I can have two cases to be set, positive, negative, as well as 0, right? So I'm writing here case 1. So case 1 is, or case actually -1, because +1 is nothing but a positive value. Case is -1. We will have to print as error. Then we have case 0. It is child process. And then we have default case. Why? Because the ID won't be only 1. It is just a positive value. So we can't write all the positive values. So we are writing default. So default is nothing but your parent process. Okay. Now this is your, when you are executing your main program, what happens? This is your parent program, and when you are executing your child, it will copy the whole program into your child process, but it will start execution from this after fork. After fork, whatever is there, it will start execution. Okay. Just to show you do this, I'll just write even whatever when we create the scope, what is the PID of it. Okay, we use one function called getPID, right? So we will print that also. So in our main function as well as in our child function, sorry, process, not function, child process as well as parent process, what it is showing, we will see PPID, oh sorry, PID. PID as well as PPID we will see. So percentile D, say this is PID. Okay. PPID equal to percentile D. Get PID. Get PID, comma, get PPID. Now this also should execute 2 times. Why? Because we are writing this printf function after 4. So my main process should also execute as well as my child process should also execute these 2 functions. These 2 times it should use this print. Now if we execute this program, here, so we have an error, expected semicolon. I have not given semicolon before. This is nothing but compile time error, which our, okay, here I have not given semicolon. GCC is giving us. See, the PID of the created process is 3621 and the parent process of our main program is 17, yeah, sorry. This is child process and child process PID is 3621 and the parent, that is our main what process, that is our 1718 parent process. Okay. Now it is not necessary that which process will execute first. Even though you have parent as well as your child process, it is not necessary. It depends on your compiler that PID it is displaying sometimes. 7 parent process as well as your child process. Parent process and then child process, and that's why here we don't have the same PIDs or PPIDs. Actually, what should happen? The child process PPID should be same as your PID of parent process, right? Child process PPID should be parent process PID. But here we are getting different because first the parent process is executed and then the child process is executed. Okay. So whatever we want to use that particular, whenever we want to execute different particular functions, we will have to give it in something like if else switch conditions we can write that will be created, executed by our parent as well as child. Mostly we go for conditional statements. Now, we will write one more program. Now, here we are introducing one more function called exit function. So first we will just execute this program, and then we will see what this about that function. Okay, here we have undeclared. It is there in std. Exit is there in this std.lib.h. And I am declaring one variable h. Now which has executed /a.out. Now it executed child process. Okay, it executed only once. Okay. Now what happened here? First of all, we will see this exit code. So we will just use this manual for exit. Here, exit. Now, why? What does this? It executed only once, but actually, our after scope call, what happens? It is the same program is copied in your child also, and it will execute it 2 times. Okay. So obviously here second time it will not be executed because in main function your ID is not 0 but the ID contains the PID of your fork, right? So anyway it is not going to execute. But what does this exit cause? Exit cause normal process termination. It will terminate the process. Okay, and it is there in your std.lib.h, and as we wrote this exit with an int status. It can have, and this is 1 byte. Okay, so as it is of 1 byte, you can have 255, 0 to 255 values, integer values in this, like exit 1, exit 2, exit 0, exit 5, exit 255, like that. You have different values it can take. So if we see the next things here, then the description. So when it happens, it will return the exit code to your parent process. If you see, status and 0ff is returned to the parent process. Then other thing. Okay, that's what we can find out here. Okay, so exit is just for your normal code termination. Now suppose I want to know that whether my child process is executing this particular block of code or my parent is executing that. Now I don't want both the child as well as process to child as well as parent to execute the same code. But how do I make sure that if at all if it is executing both, how I will know that this is executed by parent or this is executed by your child? So there what we can do is we can just have a exit value. Okay, so if we have this exit value, we can just, or we can say that conditional statement return values. So if we have this return values or exit codes, we will understand that this is executed by our child or this is executed by our parent. Okay. Now here also we are using that same thing. Now if we say, sorry, not this code, but okay, if I write here else condition, already we have done it in process2.c. I think I'll just see that. Process2.c. Now if we do not equals condition. If we see here also if as well as else condition is given, right? So here we are using this conditional statements to find out that whether we are executing your child process or parent process. Now suppose here my parent finishes our task. I said you it can always execute anything, like your parents will execute first and your child can execute later. Okay, so my parents will finish the execution first. Then what happens if the program exits? Your child process becomes orphan, right? So in that case, what we have to do is we are using something like blocking state. So that blocking already, or we can use wait for the child to finish the particular process. So to wait, we need a blocking statement. So here we have used something like sleep. Okay, like that you can use any blocking statement just to wait for your child to finish the process first. Okay, so we have seen that. Now if I don't use this, then what happened we have seen. It didn't execute it properly. GCC process 1. Here still it is simply it executed only child process. So as soon as the child process executed, it simply stopped executing. it is it stopped executing. So here, that's why we are just using one blocking statement to say that yes, wait till the program finishes. So we will have to use some blocking statements for that. Here we have blocking statements. Generally we are using are either scanf or wait statement. Okay, so these are some blocking statements we are using. So now what happens when your child process finishes or terminates? Then in parent process, this wait will come out of the blocking state. Okay, it will wait till the child process execute. So as soon as the child process finishes its task and return to the main function or parent process, this wait statement will come out of the blocking state. So when we say something like sleep will come out. There we have written sleep of 1. So here it will come out of the blocking state every 1 second. Okay, so it is waiting for your child to finish its task. If it is not finished, then again it will go to that particular child process. So first it will just wait. As soon as it finishes, it will just wait. After waiting, then it will continue its operation. And when we say scanf, what happens till we enter some value from keyboard or any external device, it will be in the blocking state. As soon as we enter some value externally, the blocking state will be it will come out of blocking state. So now here we have to, if we are using child process, the exit statement, whatever we have written has to be mentioned at the end of it, end of the if block. And one more thing, here this wait statement can be used only by parent. Child process cannot use wait statement. Only parent can wait. Child cannot wait. So when you are waiting, then just to make sure that exit has to be there in child process. Okay, when you are using wait statement, we have to use exit statement in child. Why? Because our parent is waiting for child to finish. So as soon as the child finishes his task and come out, exit, then the wait of parent will be over. Or if we don't want to use this exit, at least we have to use this return. Like generally we are using our return function. Now, so if at all the exit value is 0, if the exit value returns a value 0, which means that it is successful. Okay, and if it returns any value other than 0, in between 1 to 255, because it is a 1 byte, that means we will have 0 to 256 values. If it returns anything other than 0, then it is failure. Now, what happens once the child process terminates? That means it returns to its parent process. So when a child process is terminated, the memory segment which is created in user space. Why? Because here again two process means two different memories will be allocated. So when the memories, then the child process terminates or returns to your parent after successful execution, then what happens is the memory segment which is there in user space is deleted. PCB will be there, it will not be removed immediately. Okay, but then what does this contain? And one more thing also it will store. So once the child process is terminated, user space is deleted. User space is deleted, but kernel space PCB will be there, as well as it contains one more information, and that is exit code. What exit code it executed. So that information will be there in PCB. It will not be removed immediately. Then what happens? Your child process terminated, the memory got offloaded, and then but still the kernel space PCB is still there in your memory. Then the kernel will send that child process exit code, whatever exit code it receives. So if it is something like 0, so this PCB, what the kernel will do, that is, kernel will set this exit code to the parent process. Okay, it will have to inform, the kernel have to inform this information about termination to parent. How the parent will understand whether the child has child process is terminated or not. So as with this exit code information stored, your kernel will send that information that the child process is terminated. This information to parent will be sent through kernel using this exit code. Now if the parent process receives this exit code, then it will resume its information. Why? Because we are using this wait statement. Okay, so then this will be this, it will come out of this particular state. Now suppose what happens is actually when your functions are big and each process CPU will allocate some particular amount of time. Okay, now before executing that particular child process, if the CPU time allocated is finished, so it will go to parent process and the parent process will start execution. Now when the parent process is executing, at that time the kernel will not be able to give the information to the parent that the child child exit code will not be, the kernel will not be able to give the child exit code to parent because the parent is busy with the execution. Right? Is it clear? Okay. So the kernel will not be able to give that information to the parent. But when the parent becomes free and then the kernel will be able to give that exit code to parent, regarding this child, then only the PCB of that particular child process will be offloaded from user kernel space of RAM or from memory. Okay, what we said, the child process once terminated, will the memory of that child process allocated will be offloaded from user space, but still it will be there in kernel space of RAM. Once the kernel gives the information to parent that the child got terminated and the exit code is given to parent, once the parent receives the code successfully, then the PCB of that particular child process from kernel will be offloaded. Okay. Now, when the memory segment of the child process, as I said, the child process is, parent process is busy and it cannot receive that exit code of the child process, it will not be able to receive. Now, here you have, now the process, the memory segment of the child process from user space is deleted, but still it is there in kernel space of RAM. Then that is called zombie process. Okay, what is zombie process is memory segment child gets offloaded from user space of RAM. Okay. From user space of RAM, but the information remains, or you can say PCB remains, or the memory segment get offloaded from user space but remains in kernel space. Then this process, what does kernel space contain? That the PCB of the child process, right? So the memory segment of the child process gets offloaded from user space, but it remains in kernel space till you give the exit code information to parent, right? If the parent is busy, then it will have to wait. Okay, that wait can be used by when a parent calls wait function. Okay, so here till that time that PCB information will reside in kernel space of RAM. Okay, the child got terminated, user space of RAM is not present for that particular process, but kernel space of RAM is occupied by that particular process, then you call that particular process as zombie process. Okay, if we want to see the zombie process, we will have some command called ps-ef, et, sorry. So here we can see the zombie process if we want to see the information regarding it. Now we have discussed something like orphan process as well as zombie process. So orphan processes, if parent finishes task and terminated, then before child without using this blocking statements and it exits the process. At that time child becomes orphan. And zombie processes, if the information or user space of RAM for the particular process is offloaded but is still there in the kernel, then you call it as zombie process. Now, here you have one more From that time we are using one statement called wait, right? So when you are using this blocking statement wait, what it will return? It will return the PID of the terminated child process. Okay, so here you are waiting. So once waited, it will return something from your child process. So what it will return? It will return PID of the terminated child process. Now, next, here we have one more thing called so here we will write one more program now. Now what happens here when we use this? if we are using this, first of all we will have to take this variable also. Now in this process we are creating two child process. Okay, so here we will have to wait and then we will print. Now, first here we are using some variables and so here let's close this. Okay. Now we are creating two processes here, and one process will wait or will sleep for 60 seconds, and the other process will sleep for 30 seconds. Okay. Now how it will execute first we'll see that, and then I'll explain this process. Now implicit declaration of function wait. Okay. No problem. Now, first the second child is executed 2 times and then the first child is executed. And it is waiting. Why? Because 1 minute is not over. Now we will have to wait for 1 minute because we have given 60 seconds. In case of that, I would have given 30 seconds. That would be better. Now, after 60 seconds, it got terminated. Okay. Now, why the second child executed first? Why? Because here it started executing this. Okay. And then it is waiting here for 60 seconds. So, in this 60 seconds of time, this executed 2 times. Okay. And when you see this program, this fork is again called in your child process. That's why it executed first this and then it executed first child. Is it clear? First, after creating a child process, it will go to first child process. In first child process, again we are creating one function called fork. So after seeing that, it executes printf function first. Now, if you have simultaneous process and if you are using some functions at that time, there is a possibility that we don't know which child process is executed first. After exiting this, then only our main actually we didn't display this also. We will have to see this also. Wait, process, wait. What else? We will write this in place of, we will just write a wait function and then we will write printf in that function. It will execute what it is showing. So here the wait will show the status of your, it will show the exit status. Okay. I think this program might not be clear for you. Why? Because it is executing first the second child. But here if you see, I'll just write here 20 seconds, or I will write here 5 seconds, and then we will write here 1 second. Sleep is for 1 second and then exit. We will have to write this wait function. We will write it. Now see, here the CPU time allocated was depending on first it executed second child. The CPU time allocated was finished and then it went to first child. After 5 seconds again it came to second child and it executed. So it depends on what is the blocking state or sleep time you give, depending on the size of your or the time allocated for CPU to execute, the second child or first child will execute. Now if you see the first one, there the 60 seconds were given. So in that, before that 60 seconds, here that second child executed 2 times. But here if you see, the second child and after that first child and then again second child is executed. So all it depends on the sleep. Okay, and why this second child executed 2 times is because the child process, when you copy the first the child programming child process, again it is calling one more fork function. So one more child will be created for first child, and when it returns again, your main process will also execute one second child program. So here 2 programs are executed. One child process, once it is executed by your first child process, and the second child it is executed by your main process.
Oh.
So these were some of the topics we have today. We will continue it tomorrow now. Okay. So tomorrow again we will see some more programs. Okay.
Oh.
I hope till here it is clear.
Yes.
Or is there any confusion or okay. Till here it is clear, right?
Yes.
If you have any errors, do ask. Sorry, not errors. I'm saying errors. If you have any doubts, just ask. If not, okay. We'll continue it tomorrow. I hope this is clear. So we will just finish this off soon. Maybe today is Friday. Maybe by next Tuesday or Wednesday, we will just finish this particular basics of your Linux Essential module. Then we will go to some other module. Okay.
Oh. Thank you.
Oh.